Welcome to the Nanovation Podcast. Information about this and other episodes can be found at fillerlab.com/nanovation. If you like what you hear, be sure to tell a friend or leave a review at Apple Podcasts. It really does help. I welcome your thoughts and suggestions. You can contact me on Twitter at Michael Filler or via email at nanovationpodcast@gmail.com. Thank you to the Chi Foundation for their generous financial support.
We micro-nano-machine it to try and define devices out of that. And the first three devices that we demonstrated out of this technology are a microelectrode array, a microneedle, which actually is the simplest device because you can just go from a design to a fully 3D printed microneedle within a matter of literally minutes, and microfluidics, which combines a 3D printed base and either a laminated insulation layer. And we demonstrated applications with all these three devices in three different areas.
That's Swami Rajaraman talking about his laboratory's work on microelectromechanical systems, or MEMS. MEMS combine miniaturized structures, sensors, actuators, and microelectronics into a single device. Swami's laboratory develops new MEMS fabrication techniques for the advancement of human health and personalized medicine. In this episode of the Nanovation Podcast, Swami takes us on a journey from his days as a graduate student at Georgia Tech to his time as an early employee of the startup Axion Biosystems, and now as an assistant professor at the University of Central Florida. Along the way, Swami provides great primers on the state-of-the-art in MEMS and 3D printing technology. Swami is a serial entrepreneur, at one point in the show mentioning his struggle with the choice between life at a startup or in academia. Both career choices are deeply entrepreneurial, and if you've ever wondered about one or the other, this is the show for you. This is the Nanovation Podcast, an exploration of big innovations emerging from small things. I'm Mike Filler, your host and a professor at the Georgia Institute of Technology. Enjoy the show. Well, it is my pleasure to welcome Swami Rajaraman to the podcast. He is an assistant professor at the University of Central Florida, has a really wide array of experiences in the nano space in a lot of different technologies. So he'll talk about that. So let me first say welcome to the podcast.
Thank you, Mike. Absolutely humbled and honored to be on this wonderful podcast.
Well, great. We're really happy to have you. So like I said, you're a professor at the University of Central Florida. You've only been there for a year or two, or a couple years, right?
Yeah, the coming up in August is going to be the wrapping up of my second year at UCF.
Okay. So you just got there, and you're hopefully have a lab, and you have a couple students, and things are just getting rolling.
I do. I don't know. I mean, I feel like maybe because of my prior startup experience, which I know we'll get to, I think I was on the impatient and let's get going fast track.
Right.
So I have one postdoc, two PhD students, soon two master's students, a couple of undergrads, a couple of exchange students that have already gone through with their 6 months bachelor's thesis program. So, yeah.
Okay.
I've been busy.
So tell me about all of your joint appointments. You have a lot of joint appointments.
UCF is one of the biggest schools in the country, and I did not know that till I came to interview in Orlando 2 years ago. So they're obviously an emerging engineering and technology school, and my primary appointment is actually with a research center called Nanoscience Technology Center. And the history of it is about 12 years ago, I believe, the state of Florida came in to all the universities and said, we have some extra money. So why don't you guys propose something unique in an emerging area in science or technology? And we have this money that we can actually give you. And UCF, University of Florida, South Florida, everybody proposed. And UCF's idea on building a center around nanoscience and technology, soon to be developed, hopefully, as a department and then as a college. And I think the College of Optics in UCF played a critical role in this getting awarded. So this was awarded. So it's been so my primary appointment is with this center where it's 23 faculty members, very, very interdisciplinary people like me who are electrical engineers, micro nano engineers, essentially, people with a lot of material science, people doing a lot of quantum dots, nanowires, and then like people doing surface chemistry, people doing biology. So very, very interdisciplinary. It's still not finalized yet, but it was a 10-year awarding center, which is unique. But now that's going to change, and we are all going to be asked to go to our home departments, if you will.
Oh, is that because it's going to be sunset as a center, or no?
The center is going to continue,
okay.
and the Institute of Electronics and Nanotechnology at Georgia Tech comes up often in the discussions of how we should model and try to emulate something that we can aspire to be in hopefully 10, 20 years.
Right.
But that's the idea. It'll still be an interdisciplinary research center with shared facilities and shared resources, but everybody will have home appointments in chemistry or material science or electrical engineering or biomedical sciences, etc.
More of a traditional setup.
Exactly.
Yeah.
So around the same time I was interviewing, there is also this University of Central Florida is a big investor in this not-for-profit foundry, if you will. It's called Bridge. It's the acronym is Bridging the Innovation Development Gap, originally called ICOMAR, which stood for International Consortium for Advanced Manufacturing Research. And that is a very unique 8-inch foundry setup. It's coming up in Kissimmee, Florida, which is about 40 minutes from the UCF main campus. And I have a joint appointment with them. I'm still trying to figure out what that exactly means.
Okay.
Other than participating in some of their technological exploration and setup. And the clean room is getting set up right now. Actually, the first wafers will be through the fab in August. So that's that one. The other appointments are with the departments that I'll have to pick from, electrical engineering and materials science, joint appointments, secondary joint appointments. As my home department to go up for my tenure and other things.
Right. Well, it's never a bad thing to have choices. So the Bridge thing is an interesting one, and it's in Kissimmee, and a lot of people would say, wait a minute, there's a place in Florida where they're doing a lot of semiconductor manufacturing. Can you talk a bit about how that nucleated?
Sure. So the history of Bridge, I think, comes a little bit from people that were in the veterans of the semiconductor industry that were in Semitech. And when Semitech Austin, I could be getting my history wrong, you probably know this better than I do, closed up or was about to shut down, some of the senior management moved, or they had plans of moving for personal reasons or what have you, to Florida. And they were able to pitch this idea to the different universities, to the state government in Tallahassee, and they were able to get this pretty substantial startup fund. And it was pitched as not an academic entity, not a commercial MEMS foundry or any type of CMOS foundry entity, but it's something that is going to be in between, where it's going to take technologies from the university into the marketplace, and it's going to be not for profit, so it's going to be funded essentially by customer projects and company projects. So we need this initial investment to set up this 8-inch foundry. So that's how it's got started, I think, three and a half years ago. So it's still very new. We are still getting our name out there. The technological platforms that we want to work on are still being narrowed down. I think we have a few platforms now. But it's sort of building up. As a staff about 30, 40 people now that have, and the facilities, initially it was just a pitch and a drawing and, saying, hey, there is going to be a nice little fab here in the future. But the facility is fully built up. The tools are getting set up and they're starting to move wafers through the line right now. So still a long way to go, but exciting new foundry setup and a nice little idea of not being all profit or not being all academic, but sort of being somewhere in between.
Yeah, and I'm a big proponent of bringing more things to the Southeast U.S. I think we're just getting rolling here in the Southeast.
Me too. Me too. All my years in Atlanta and now in Florida, I'm a big fan of the Southeast, and yeah, definitely a huge proponent of bringing more stuff down here, more high tech down here.
Yeah, so Bridge sounds a little bit like IMEC or the Danish Technological Institute, where they interact directly with companies. I was going to ask, and maybe you just said this and I missed it, does Bridge have base funding from anybody, or do you have to have a project with some company to do the work?
So Bridge does have base funding from, the reason they're in Kissimmee is because Osceola County, which is where Kissimmee is located, gave a lot of land in kind, essentially. So they have a lot of base funding to set up and buy tools from the state and from the different universities, and UCF has invested a lot of money into it. And then they have this land in kind from Osceola. That's why it's located in this area. And the idea is to bring it's called Neo City. We even have a zip code, Neo City, Florida, where you have using this as an anchor to build a whole high-tech industry there. But right now, they have been having a lot of conversations, and I'm honestly not privy to a lot of that information because my primary appointment is still at UCF and as a faculty member at UCF. But the idea would be that you would have a project, and can be in any form. You could be a company that could come in and say, hey, I want you guys to do this and scale this product up into production, or you could write a grant with Bridge to an SPIR, an STTR kind of grant with Bridge. So any of those models of bringing new types of projects and funding into Bridge will work, as long as it's something where, you win and Bridge also has something out of it.
Okay. I'll put some links to Bridge and to Neo City, which this is all news to me. It's fantastic. This actually, the Neo City website makes you want to go visit. There's it's like a great waterfront and a beautiful bridge, and looks like beautiful places to work and eat.
It's all getting set up. Just
okay.
Right now there's only the Bridge facility, and IMEC is actually the first. IMEC has a new design center where they're building photonic circuits, and they're hoping that would be fabricated in Bridge.
Okay.
So they're actually co-located in Bridge, and they're the first essential customer, if you will.
Well, very cool.
Absolutely. You're welcome to come anytime, just as a side note, and we'll happy to show you around UCF and Bridge. As I said, the Neo City vision is fantastic, but there is Bridge and IMEC, and there is nothing else right now.
Okay, so we can decide how close we are to the vision laid out by the graphic designer, right? The graphic artist who put together the picture I'm looking at on the website. Okay, but thank you for the invitation. So let's talk about where you got your start in science and engineering. As a PhD student, you worked in MEMS. So why don't you talk about what MEMS are, what they're used for, and at some point kind of throw in why we can consider them pseudo-nano. Because it is a podcast about nanotechnology, and I stick to that loosely, but we should try our best to make a connection there.
Absolutely. So, I did most of my work even before my PhD in MEMS. So I got my start doing my master's actually developing silicon microneedles. And then I actually worked for a MEMS company in Boston for a couple of years called Analog Devices. They are the preeminent, or one of the preeminent MEMS companies. They were the first to commercialize an accelerometer manufacturing line. Accelerometer sensors are used. Their primary application at that time was airbags when they commercialized it in the 90s. But of course, they are now used in everything from your iPhones to your smartwatches to drones to so many other areas. The project I was involved in was on optical MEMS. We were developing both CMOS integrated and standalone MEMS micromirrors. They're about these 800 micron mirrors that can be either analog, where they can essentially tilt in specific angles and can be controlled by CMOS circuitry that was in the vicinity, or completely digital, where they respond to, essentially be completely closed or completely open to let light in. So that's where I got my start in MEMS, doing a lot of silicon micromachining. And to most people, MEMS still means accelerometers, gyroscopes, resonators, these micromirrors that Texas Instruments has commercialized, and you can see it in our projectors and other products. So to most people, it still is a silicon micro machine device.
So real quick, let me interrupt for a second. So then what, for someone who has no idea what a MEMS device is, can you explain what it is, like, say, relative to an integrated circuit? They're both built in silicon, but what makes a MEMS versus integrated circuit?
That's a fantastic question. So MEMS stands for microelectromechanical systems, right? So I think it evolved from CMOS integrated circuits by introducing a third dimension. So you not just have the ability now to move electrons and current in X and Y, but now you have your third dimension through which you can actually get micromechanical motion. You can use this circuitry, for instance, to control this micromirror in the Z direction. So that's where in the MEMS got started in the 60s and actually got formalized as a community in the 80s when this gentleman by the name of Kurt Peterson wrote silicon as a mechanical or micromechanical material, was this IEEE paper that he wrote that sort of brought a lot of these diverse concepts into taking integrated circuits into the third dimension and starting to see both mechanical motion in combination with essentially transistors and passing currents through devices. But since the field has dramatically evolved, it has evolved, and to a point when I think I mentioned that in my email to you, I don't even touch silicon anymore. A lot of work in the MEMS field, especially in the 90s, and has accelerated in the 2000s and the 2010s, is going further and further towards plastics and different polymeric substrates where you can create different types of devices. Not in all cases having that micromechanical component, but sort of driving this manufacturing technology capability into and taking some of these silicon micro nano machining concepts and trying to transport it into non-silicon type substrates. So and to answer your question about where nanotechnology comes in. So, for instance, over the last 10 years, I've been developing microelectrode arrays, and I'm sure we'll get into what those are in a little bit. And with microelectrode arrays, you're trying to interface with electrically active cells like neural cells or cardiac cells or stem cells or muscle cells or retinal cells, both inside the body, on the body, and outside the body. So anytime you have that sort of an interaction where you're trying to measure these sometimes really, really small electrical signals that can be, in some cases lower than 5 microvolts peak to peak, you need surfaces that have very high surface area. So all the electrodes that I have built over the years have a nano component. They have a nano material or a carbon nanotube or something that gets defined in the electrode area that's typically anywhere from 10 to hundreds of nanometers that enables some of these functionalities. In this particular case, this reduction in noise so that you can have higher signal to noise ratio for effective transfer, effective transduction of the signal from the cell onto your device and then onto your circuit.
And I was going to say, even more generally, I didn't say this at the beginning, but MEMS have led to what people call NEMS, right? Which would be nano electromechanical systems. And so as we've gotten better at doing MEMS, things have just shrunk. And so we've kind of encroached upon the nanoscale in lots of different things. You're giving a great specific example also, but just generally speaking, like what we saw in integrated circuitry, things have gone towards the nanoscale over the last several decades.
Absolutely. That is so true. I think starting with, I gave an example of a practical example of what I'm used to or what I've been, developing over the last 10 plus years with microelectrode arrays. But yeah, in so many other fields, the push is everything from interconnects to these nano electromechanical resonators and other types of traditional silicon MEMS devices. Yeah, the push is definitely towards nano. And even in some of these newer areas that I'm seeing, like I mentioned in my email with you, like paper and plastic MEMS, and I can talk a lot about how there is push in neural MEMS to get towards the nanoscale and why that is important. But the push is definitely towards getting into that, and some of these non-traditional technologies have also caught up and are doing, I talked a lot about 3D printing, and we can talk a lot about that because that's what my group does quite a bit now. But even there is definitely a tremendous push towards getting smaller and smaller feature sizes for better sensitivity and, lower, much lower amount of liquid or, bodily fluid or what have you required in order to sense and to get your specific sensing signature from.
Awesome. My next question was going to be what's exciting in the field today, but you've kind of talked about that already, and I think we want to talk about it also a bit in context with what your research group is working on. So before we get to that, though, let's talk about you moving from your PhD work to startups, and you've worked at several. You've worked at Axion, CardioMEMS. Let's start by asking what attracted you to the startup world.
Oh, that's a good question. So I always think of myself as one of those people that can never make up my mind between academia and startups. Initially, I was going to say academia and industry, but I think I'm definitely drawn towards the smaller scale companies and the excitement and the product development pressures and things like that are inbuilt in there. So I started off, like what you said, during my PhD days, interning as a graduate intern at CardioMEMS, which is implantable MEMS pressure sensor company. So it's the pressure sensor is essentially has a diaphragm, and in this particular case, we were developing what is called a passive resonant LC circuit. It's an inductor and a capacitor together, and the capacitor diaphragm moves up and down depending on the pressure that it's implanted in the wall of the artery, and depending on the pressure that's put on it by the flow of blood. And that's where it comes into detection of detection of heart disease, congestive heart failure, and that's the application that they have commercialized. So it's essentially actually it's a nano. It's a microscale diaphragm with nanoscale motion. The motion is it's sensitive to nanometer scale motion. And the gap between the capacitive plates actually is roughly a micron, or in some designs even lower than that.
So is it as simple as when it senses a lower pressure, your heart is not able to push blood as effectively?
So it senses what is called a baseline resonant frequency, right? So you can calculate, if you have an LC circuit, based on the dimensions of the LC circuit and the capacitance and the inductance of the devices itself, you can calculate the resonant frequency. And so it calculates a baseline resonant frequency when it's implanted, and any shift in that resonant frequency translates to there being some trouble and blood having to work extra hard to get around that trouble. So that it's a diagnostic device that starts to sort of track the progression of heart disease. So anytime there is an obstruction, for instance, your blood pressure builds up.
It would go up, right? Okay.
And your resonant frequency changes, and it's something that has been gotten to a point where patients can monitor on a daily basis now by themselves.
Right.
So it's actually a pretty neat idea where you have the LC resonant circuit being powered from the outside by an antenna. And so you can measure it with this antenna at home, and that all that data, and they've done a lot of work in trying to get all that data directly onto your doctor, and him or her being able to monitor that on a daily basis. So back to my experience with them, I was a graduate intern. The company started, I think, in 2001 out of Mark Allen's group, who was Regents Professor in Georgia Tech, my former PhD advisor now at University of Pennsylvania. And at that time, when I first spoke to Mark, he didn't really have a project. And he was like, you seem to have some experience, so why don't you go work with this company that just got started from my group? So I worked with them for a year. I developed some key microfabrication processes in this LC passive resonance circuitry that I talked about. And then I was always interested in getting my PhD. So I came back to his group when he had this student graduate on this NIH funded project on neural MEMS. So I was always interested in biomems and biological nanobiosensors and biomems in that space, moving much more from mechanical and resonance structures more onto measuring stuff on the body. And he had this very interesting NIH-funded project where the student had just graduated and there was still a few years of funding. So he wanted me to start exploring three-dimensional MEMS technologies for three-dimensional microelectrode arrays. So that was my PhD thesis, was development of multiple fabrication platforms, mostly on polymers, to develop 3D microelectrode arrays. So when I was getting close to finishing up, there was one of my colleagues who worked on the same project with a different professor at Georgia Tech, was interested in commercializing some of the CMOS circuitry that he had developed and his group had developed, and some of the MEMS technologies my group Mark's group was developing. And I was sort of in the middle of all of that, and Axion Biosystems sort of got started organically from this NIH project in 2008 when this student, his name is Jim Ross, who graduated from it. He's still the CTO of Axion Biosystems. So I was also graduating, obviously, into my original intention was always to get into an academic position right after my PhD and start building my own research group. But as you know, 2008, 2009 was not the best of times. Hiring was on the low almost everywhere. At that point, I was still an international student. And, some of this organically started with the company, and the company was able to get some quick SBIR type funding pretty quickly. So I saw an opportunity there, and I was like, oh, maybe this is something that I've worked with CardioMEMS, but CardioMEMS was already at like 30 employees when I joined in, and had a couple of rounds of venture capital funding, whereas Axion was just starting up, and I was one of the first people. I was actually part of the founding group. So I was like, this will be very, very unique and neat experience that I could probably leverage for the future as well. So I got started, and after finishing my PhD, I worked full time for Axion for the next 5-6 years before I got back into academia again.
Okay. So a couple things. I think we crossed paths multiple times when you were on campus. I'm assuming Axion was developed, on Georgia Tech's campus.
Yes, actually, we were in the incubator in the same. You're sitting in the. Your office. I think I've seen you multiple times.
Yeah. I think I saw your picture, and I was like, I've walked by him a lot of times.
So
that was the first thing I wanted to say. I wanted to go back for a second to the CardioMEMS thing and say, when you sent me the link, and I'll put this in the show notes, this system, at least as far as I can tell, is today called the CardioMEMS HF system. HF meaning heart failure monitoring, as you described. And I saw it. I said, CardioMEMS HF system. HF, why are they putting hydrofluoric acid in this? Right? So to someone who works on semiconductors all the time, I was like, this is a horrendous name for something you're going to implant into your heart. But okay, that's a side point.
I actually used a lot of HF because the sensor is based, if ever for a second, sensor is based on this two wafers, two fused silica wafers that are bonded together, and you etch trenches in both of them, and we used a lot of HF, both dilute and highly concentrated HF in our fabrication.
Yeah, I saw that. I said, okay, it's not what they mean. So let's talk about Axion. There's a bunch of cool sentences, and I'll read one of them. If you go to Axion's website, the headline says, "Explore Life's Circuitry," in big letters, and then it says, "Excitable cells play a fundamental role in life, from heartbeats to brain function." So can you talk about that a bit, what that even means, and then what Axion and what these kinds of microneedles help you do?
Sure. Axion, that is a very catchy and a fundamental marketing line that I believe that they have, the Explore Life Circuitry that they have trademarked. So essentially what they mean is an electrically active cell, electrogenic or excitable cell, can be anything from, as I said, neuron to cardiomyocyte. Those are the two main areas that they are playing in, or a cardiac cell and a neural cell. But you can think of muscle cells are electrically active and excitable. Retinal cells are electrically active and excitable. All the stem cells that are coming out are electrically active and excitable, or can be made electrically active and excitable. So what it means by saying excitable is if you break this cell down into its cell membrane and what is really happening inside it. So if you take a neural cell, for instance, on the cell membrane, it has a bunch of ion channels that are exchanging ions between the outside of the cell and the inside of the cell. And based on these ionic currents and the constant flow of ions in and out of the cell, you can actually measure this constant flow of ions in and out of the cell. So the traditional way, and this was discovered in the 1950s, that electrically excitable cells in the brain and the spinal cord and different parts of the body that actually control a lot of the functions actually have these ion channels, nanoscale ion channels on the outside of the cells and ionic flow. And you can actually measure these, picoampere currents, if you will, from these ion channels. But what has been realized since then is a single level observation of these ion channels and cellular activity is important. But if I take the specific example of a neuron, they're also constantly making connections and communicating with each other, right, through axons and synapses, which are actually signal transmissions that go from one neuron to another. And this network level activity in a lot of cases is far more important than your single cellular case because, in the body, we have very, very complex organs like the brain that have 86 billion with a B neurons and 85 billion support structures that also play a role in the signal transduction. So as you start building this circuit out and as you start measuring these what are called extracellular action potentials, which is a coordinated activity of these ion channels and how they are communicating with each other, that becomes a lot more important. And that's where all the explored life circuitry and monitoring and manipulation of these signals becomes very, very important in a whole host of different functions, from anything from the effect of drug variations on cells to things like nanomaterials and the effect that they have on some of these synaptic connections, to like modeling diseases and even modeling organs on an individual chip. And that's where the field is essentially going. And what Axion does is it develops instrumentation and microsensors with nanomaterials for that low impedance metric that I mentioned before. And what customers of Axion do is they take these electrically excitable cells, either from human sources or from animal sources, and they actually culture these cells on these dishes. And they monitor and sometimes even actively engage with the instrumentation and with the CMOS circuitry and with the sensors and all the functionality that has been enabled to create some of these more complicated disease models and organ models. If that makes enough sense, or if you want me to go and explore any one of these, please.
Yeah, no, it was a really good description of, at a high level, what's going on. You have a bunch of cells, and they're interacting with each other, and you want to understand those interactions. And so this is a technology that allows you to do that. So this is something that I guess research labs would be using, or companies doing product development would use, drug development would use, et cetera, right?
Exactly. So when the company started, the idea was, and I was listening to your interview with Bara Kola yesterday, and some of the things that he talked about from translation. So initially, we were all excited about technology. We were like, oh, we're going to do this 3D MEMS. We have this very unique ASIC circuitry that can actually, with which you can both stimulate. So when you stimulate a specific cell, you have what is called a stimulus artifact that obscures the ability to record. It essentially blanks all the amplifiers, not just the stimulating electrode, but also neighboring electrodes for quite a while. By quite a while, I mean, tens of milliseconds, but that's still very, very important. So Steve DeWert's group at Georgia Tech had actually developed the circuitry that actively discharged this stimulus artifact. So you're able to do simultaneous stimulation and recording. and do all these 3D MEMS was what the initial vision was. But then as the company grew and we started interacting with not just academic researchers, but also industrial researchers like pharmaceutical companies and stem cell manufacturers and things like that, it became much more about throughput.
Okay.
It completely reversed because MEAs were usually 64-channel devices, just 64 electrodes, one culture well, so one experiment at a time kind of devices. So Axion came out with this concept of taking that and developing high throughput, not just devices, but also interfaces. So the Axion standard device has 768 electrodes that are distributed in 12, 24, 48, or 96 wells of electrodes. So throughput became the name of the game. And right now that's, all that they're doing is trying to take this throughput and try to integrate more new functionality, more new software, more new robotics, because there is, as they found out over the 10 years of existence, there is a lot of demand for increased throughput in drug screening and toxin screening and stem cell development and so many other fields.
It's a classic case of what happens when a technology hits the real world, right? This is
Absolutely.
So frequent that you have this idea of what you're going to do with this. You start a company and you realize really quickly that either it's just never going to work, or to be viable, you got to go after a different target.
Exactly. It's that is so true. And the way the company started, we were making, so there are competitors to Axion, and the main competition at that time, there's a few more that have come up, was this kind of German company called Multi-Channel Systems, and they had made a living making these single sample devices for 20 years before Axion got started, or 14 years before Axion got started. And when this multi-well high throughput format was introduced first in 2008 or 2009 at this neuroscience meeting, they literally laughed at us. They'll be like, there's going to be no real market for this.
Yeah.
And as the company evolved and started talking to more and more people, especially these research labs and pharmaceutical companies that were doing high throughput screening, it became more and more apparent that there is a clear market there.
Right. Okay, so you worked there for several years, and then you got another itch, and you realize, I'm going to try my hand at being a professor. So then I'll ask, what drove that decision?
As I mentioned before, I'm one of those people that I don't think can ever decide between the two. Between academia and small companies. So in all honesty, the first few years of the startup were very exciting because you were developing new things, you were interacting with customers, it was a small group, so you were doing everything from being essentially a technician all the way to, business development and dealing with customers to writing grants. I mean, it was all so many different things that you were involved in. It was very, very exciting. But once the product got developed, I got the impression that the company wanted to pivot more into integrating robotics and more advanced software features onto the device. And the device itself was, both from a system perspective and from the microsensor perspective, was more like, we'll just, do a few things here or there. And, initially there were plans to slowly go into wearables and to implantable devices, and all of those never really materialized beyond phase 1 SBIRs. So my personal interest was still very much in micro-nano fabrication development, especially with these, 3D structures and, going into wearables and going into stretchable electronics and using that to do a lot of interesting things, and definitely doing implantable stuff. And as the company's interest became much more into robotics and automation, which makes a lot of sense, I decided maybe it's time to pursue something different.
Okay, so then the question is, you want to do something different, but why academia versus another company or starting your own or whatever?
I certainly toyed with the idea of starting my own. I was, we had lived in Atlanta by the time for quite a while, and both me and my wife worked at Emory at that time, and we really liked Atlanta, and built up all this network. But I don't think we were in a financial position to take the huge risk and start something completely different. Mm-hmm. As I mentioned before, I was always interested in academia. I come from a family of academics. My was a research scientist and professor most of his life. So that interest was always there. And I knew that I was on the outer edge of being someone that can start in an assistant professor position, given that I'd spent 5 years after my PhD, 5-6 years after my PhD. So I was looking for both startups and academic positions, and I applied to a few, and I was really surprised that I got a couple of callbacks for academic positions. And my calculation was, in academia, you can do both.
Right.
In a startup, you still have the risk. You still have, it may go out of business in a couple of years and you're in the same position. Whereas in academia, once you're established, you can actually do both. And I decided, got the opportunity, and I was like, this is the right thing for me to do.
Okay, fantastic. So if you look at your website, you say the goal of your research group is the development of new micro and nanofabrication technologies and associated packaging technologies to address applications that advance the state of the art in human health. So yes, let's do that. Why don't you explain what you mean and give some examples?
So because of my years of experience, both developing 3D microelectrodes and with Axion, all the stuff that we did were high throughput 2D microelectrodes, I had sort of come into contact not just with clean room based technologies, but a lot of packaging technologies, and I felt like I was sort of in between the two. So with microelectrode arrays, the Axion's microelectrode arrays were large dishes. They're like about this awkward 3.5 by 5 inches in size, and you had to define all these electrodes on it. So there was a lot of packaging technologies. I built up a lot of expertise in developing a lot of packaging technologies, and the goal actually is sort of built a little bit on where the original Axion vision was going, combining some of these technologies and not just doing a lot of in vitro sophisticated models, but also doing some wearable and implantable devices. So the idea behind my research group is, again, to be the fabrication and packaging person and collaborating with a whole host of different applications people, be it that are doing fundamental material science or people that are doing biology. And I will mention as one of my examples in a minute, or people that are applying these technologies in completely new fields, like agriculture, for instance, that you can actually utilize these packaging and fabrication technologies in a whole host of different applications other than just doing neuroscience and, in vitro neuroscience and cardiotoxicity that my former company does. So that is the vision on which the group is built. And what we have in the first 2 years, what I have established, as I mentioned, there is a lot of fabrication techniques and a lot of these non-traditional techniques like laser micromachining, micromilling, 3D printing, that we use almost on a regular basis to develop different kinds of devices. So our first paper that came out earlier this year was this technology called 3D printing, ink casting, micromachine lamination. I was going for some clever acronym, but it did not come out, but it's 3D Pickle UM.
I've come up with some of the worst acronyms in the world, and you just sit there, and my wife's like, what are you doing? I'm like, I'm working on an acronym. She's like, go to bed. And yeah, sometimes they work and sometimes they don't, but we've all been there.
Yeah, so I'm initially thinking of something, pickle and combining 3D and stuff, but then, once we added components, it just became this 3D Pickle UM. But essentially, it starts off with using a 3D printed base. So 3D printing or additive manufacturing, I'm sure a lot of your listeners are very familiar with it, but essentially is a direct to design, direct from design to a fabricated device technology where you can go from a concept and a CAD design to something that comes out as a fully finished device, essentially. So we use this 3D printed base and we develop interesting structures onto it, be it things like microneedles and micro towers, or like things like microfluidic ports or spirals for some radio frequency sensing. And then we build on top of it with this ink casting, which essentially is a screen printing process, comes from packaging, where we actually take a screen printer and optimize inks that can be cast both as interconnects as well as electrode traces on these 2-dimensional and 3-dimensional interfaces that get out of 3D printing. And then on top of that, we build either a spin-coated insulation or a dielectric layer or a laminated insulation or dielectric layer, and we have played around with both. And then we micro machine that. And in some cases, because our laser has the ability to get down to 1 micron in feature sizes, and with some clever tricks, even sub 1 micron, we micro-nano machine it to try and define devices out of that. And the first 3 devices that we demonstrated out of this technology are a microelectrode array, a microneedle, which actually is the simplest device because you can just go from a design to a fully 3D printed microneedle within a matter of literally minutes, and microfluidics, which combines a 3D printed base and either a laminated insulation layer. And we demonstrated applications with all these 3 devices in 3 different areas.
So let me stop you there for a second. Let's talk a bit about the details of the fabrication, because you use a bunch of words that I know their meaning. I want to make sure everyone listening knows the difference between 3D printing and then casting and lamination.
So there is a whole host of different 3D printing techniques. The most sophisticated is something like 2-photon polymerization, where a polymer absorbs photons in 2 different wavelengths, and you're able to get some pretty intricate features with it. And that's where 3D printing at the nanoscale comes in. So I believe there's only one machine of its kind by this company called Nanoscribe that actually makes this 2-photon polymerization machines, through which you can actually go from a 3D CAD design into a nanoscale device, essentially in one step, in highly specific photopolymerizable resins.
Is this the work that came out of like Duke or something like that? Was it in the Research Triangle area? I can't remember exactly whose lab it was. Where they make like the Eiffel Tower?
Yeah. So I think it's Mike Dickey, I think is his name. He does some pretty exquisite, or his group does some pretty, he's at NC State, does some pretty exquisite 3D printing work. But the 3D printer itself, I think, came out of, the 2-photon polymerization system came out of a Swiss or a German group.
Oh, okay. Yeah, I'll try and search for the person I'm thinking of. I think where I saw this Eiffel Tower printed, I believe, with something like 2-photon lithography, where they move the stage around up and down and X and Y while they're shining light onto the polymer. Yeah. And, you can make as you're pointing out, make very intricate structures from it.
So that is the most sophisticated in terms of 3D printers, and a very, very expensive tool. When I was still at Axion, I remember Oliver Brand circulated potentially going for an NSF MRI on trying to get that tool. I don't know if Georgia Tech got it, but it was one interesting side note. But there are so many other 3D printing technologies. The simplest one is just extrusion. You take a polymer, and actually my group does some bioinks, extrusion of bioinks with it. So you take a polymer above its, in the simplest form, above its melting point, and then you extrude it through a syringe onto a needle or a micro nozzle, and then you print it on either a 2-dimensional topography or 3-dimensional topography. That's like the simplest form of 3D printing. It's called fused deposition modeling. And the other 3D printing that my group uses a lot is microstereolithography, where you have the same laser, as you mentioned, not the 2-photon polymerization, where there is more sophisticated physics involved, but the laser coming in and curing. So you have your 3D design, it gets spliced into 2-dimensional constructs. And every layer, and depending on the system, 3D print stereolithographic system that you choose, you can get some pretty thin layers of photocurable resin. And the laser comes in and cures this 2D construct, or the spliced 2D construct, in a layer-by-layer fashion, and then the 3D structure gets built up on top of that.
I think 3D printing is so awesome, and one of the things I wonder about, and it's one of the themes we explore from time to time on the podcast, is the intersection between complexity and scale. You can make these really intricate things, and for many applications, you don't need that many of them. But then there's other things where scale, in terms of the number you're actually able to produce per unit time, ends up being something that plays a major role. And I was curious if there's been any kind of breakthroughs with regard to speed and scale in terms of throughput for these kinds of technologies.
Oh, that's a great question. As far as I can tell, and I have seen, and I've been doing 3D printing only for the last couple of years, it seems like there are commercialization efforts underway for microfluidic chips, for instance. So that is one area where I see that there is clearly a need for rapid design changes, and you can actually do something, you can print it, and you're done. In terms of wafer scale sizes or larger sizes, in my lab we have done 4-inch by 4-inch. We have printed these microelectrode array chips on a 4-inch by 4-inch substrate. We have characterized what is the variability from one chip to the next, and it's not. I mean, it's still something that's evolving, and I don't think it's. You do get quite a bit of discrepancy as you go from one end of the 4-inch substrate to the other end of the 4-inch substrate. But most of the 3D printing technologies are still, you're right, stymied and more low throughput and like one-off kind of, prototyping avenues. Nothing that I know of, at least, has come up where you can actually take like a whole panel, like a 12-inch by, like a PCB kind of, 12 by 18 panel, and you can 3D print specific structures all on that panel with very, very limited variability from one to the other. I don't believe there is a technology like that.
Yeah, that's today, and I think I've learned over the years that never doubt scientists and engineers and their ingenuity to figure things out.
Yeah, you're absolutely right. I think hopefully, sometime in the near future, with some of these commercialization efforts that are already underway, hopefully that would be something that will come to fruition.
Well, actually, while we're talking about kind of the pros and cons of 3D printing, I mean, one of the other things I wanted to ask you about was the palette of materials that you have available to you. I think it started with polymeric things, and I know that's expanding, but why don't you talk a little bit about what's available, where people want to go in terms of the material set that can be 3D printed?
So there is, you're absolutely right. I think the majority of the materials that can be either photo cured or extrusion printed or laser printed, or there are other types of 3D printing technologies, laser sintering and other kinds of 3D technologies. Mostly, it's a whole host of different photocurable polymers. But metal 3D printing is something, especially with where you can actually heat up the metal beyond its melting point with a laser, and then you can either extrusion define it, or you can do with one of these stereolithographic methods. That's another area that I see increased interest in, and different types of metals. Either it's for like highly biocompatible applications, or something that's more metallic inks for soft lithographic and stretchable electronics applications. Jennifer Lewis's group at Harvard does some really nice work in that space, where they actually do, I think they make their own conductive metallic inks, and they actually develop, they wrote this great paper in Advanced Materials, I think, where they had both the ability to do these metallic inks, essentially like a package, and then place electronic components, chips, and other things with the same 3D printer, because they converted the functionality from extrusion printing of this highly controlled extrusion printing of this metallic ink to essentially a vacuum pick and place, where you would pick an electronic component and place it in specific areas. So that's metallic inks and metals are another area of growth in 3D printing. Ceramics, I recently saw an email from the 3D printer manufacturer that we use, that we have in the lab, of them introducing their first ceramic resin. So I'm very curious as to what that is and what sort of things that can be made on it. And then there is this, in biology, there is this whole new effort of trying to use 3D printing to print cellular constructs, be it for tissue engineering or neuroscience or other kinds of methods where you can accurately take these cellular constructs and place them in different locations.
That's crazy.
So
I'll tell you, that's my mind expanding, basically.
It's very, very new. It's very, very interesting. And especially in neuroscience, it's like brand new. I think there's only been a few efforts where people have tried to print neurons, and in some cases human neurons, and like actually put them, squeeze them either through media in specific combinations, either through media or through extracellular matrix materials or through biomaterials like gelatin and collagen, and actually print them in highly specific locations. It's still very, very rudimentary, and I think we can do at this stage maybe 800, 700 micron sort of droplets and different features, but definitely an area that's I can clearly see like a huge expansion in that.
Agreed. And so you mentioned 800 microns, and so my last question about 3D printing was, what are the limiting resolutions and what limits it?
So that entirely depends on the technology that you're using. So for these bioinks, as far as I have seen, most of the new efforts have been through this fused deposition modeling. So that's the printing through the syringe pump and a nozzle. So essentially, it's limited by the geometry of the nozzle, and people are starting to introduce, micro nano machined nozzles onto it. I haven't seen any dramatic improvement over this 800 micron limit that I saw with bioinks. With stereolithography, it depends. The limitation depends on whether you're using a simple mirror or you're using a MEMS micromirror. And a lot of people, Greg Norden comes to mind of Brigham Young University. They build their own custom 3D printers and custom material resins as well. And he presented in Microtask 2017 that they have been able to repeatedly produce sub 15 micron channel widths, with their highly customized multi-MEMS micromirror, which bounces the laser light and sort of collimates it and is able to, and you minimize the distortion between different interfaces as you sort of focus it in onto your resin. And then, of course, the two-photon polymerization is the most expensive technique, and I believe you can repeatedly make, on very, very specific kinds of resins, you can repeatedly make sub-100 nanometer feature sizes.
So let's go back then to the specific work that you do. That was a really great explanation of the space and limitations of 3D printing. But going back to your technology, can you explain a little bit about why combining all these approaches together into the technology that you guys have, the 3D Pickle, makes sense? And then why don't you also talk about, maybe pick one of the applications of it and kind of expand on that?
Sure. So we are basing 3D printing at the heart of a lot of different things. Another new technology that we are going to present at the Hilton Head MEMS meeting next month is actually combining 3D printing with stencil mask e-beam evaporation and using 3D insulation techniques for three-dimensional microelectrode arrays. But going back to your question about why 3D Pickle, that's the most advanced technology that we have. So the origin of it came from more thinking of the driving forces in terms of devices, specifically with planar microelectrode arrays, because I came from the company and all of that. I was thinking there is two different directions in which people are going. People are either going for this rapid design and quickly disposable, really low cost microelectrodes, and they're willing to sacrifice some level of feature definition and functionality for it. And the other direction people are going is actually CMOS MEAs. So as far as I know, there's only two groups that actually specialize in CMOS MEAs. As you can imagine, very, very complicated, and very few groups actually work on that. So my attention was drawn towards this other easy disposability kind of microelectrode arrays, given that I went through all this trouble in terms of creating these high throughput interfaces, which sometimes would take months and years to create. So we thought about that, and then we actually did this comparison with a simple glass microelectrode array where you would make a clean room glazed wafer for creating a glass chip that you would dice, and then you would pick and place assemble onto a printed circuit board, wire bond, and then do all the back-end technologies to assemble it into an injection molded culture well. And then you compare that to the simplicity of being able to do this co-design and co-development of device and package together with 3D printing. And with this 3D pickle process, what we realized was we can actually make an MEA from conception to a finished device within a matter of days, actually.
Wow.
So I went much more of thinking about the disposability route and thinking about how we can not only do that, but how we can maybe move some of these operations, given that you're interfacing with biology, and biocompatibility in some case takes precedence over some moving operations out of the clean room in some cases. So all the 3D pickle operations are done outside the clean room. If you can imagine, design, of course, CAD design, 3D printing, you can do it outside the clean room. Ink casting, screen printing, so it's just done under a fume hood. And then the baking and stuff, you just do it with ovens and hot plates. And then laser micromachining, again, lamination, laser micromachining can be entirely done outside. So the motivation was much more to try and see what sort of fidelity and what sort of device feature sizes that we can define if you take this microelectrode array as an example, and how can we compare it to this both front-end and back-end processing, which is very common with MEAs. And we did this comparison, and we are still nowhere close to the ability that you can do with lithography in terms of being able to define highly integrated electrodes with normal 3D printing. But if I had access to a nanoscribe, that'll change there. But for most of the other feature sizes, the translation from design to a finished prototype was very, very good. It actually really surprised me as to how the fidelity from design to a fabricated devices, and we compared that actually to this glass platform, and it did very, very well. So the motivation is predominantly drawn towards in that direction. With microfluidics and microneedles, there have been other reported approaches, but with MEAs and in terms of doing this completely outside non-traditional fabrication, being able to print both 2D and now 3D microelectrodes, I think we are probably the first group to demonstrate those kinds of devices.
You make a really interesting point that I think is worth talking about, and that is you're throwing out a very expensive part of the process, that is the clean room, and you're making tremendous gains in cost and speed from initiation to a final device. And you said, our resolutions aren't as good as what you'd get with lithography in a clean room. And I think this is one of the challenges of innovation. I mean, I know it is, right? That different metrics look different to different people. So you've advanced metrics of throughput and cost, and you're paying a penalty in terms of resolution. And then the idea, though, is that over time you'll get better and better at resolution, and ideally, put the cleanroom people out of business.
That's not my intention as a former cleanroom person myself. That's not. But it's something that could happen. And my argument is maybe in the narrow space that I'm looking at, which is more bio interfaces, more specifically neural interfaces, maybe there is a possibility there where some of these non-traditional techniques could take over. If we can start showing, as you said, like over a period of time, improved resolutions and being able to, there is definitely going to be the CMOS niche. You cannot compete with, my friend Andreas Herleman at ETH Zurich. I think their latest paper was using 30,000 electrodes in like a couple of millimeters. You just cannot compete with that. So there is definitely going to be that group of people. And as I said, as far as I know, there's only a couple of groups that are really doing that. But for a lot of other groups and other labs and a lot of the collaborators that I talk to on a daily basis, they're more interested in, translating their ideas quickly and, getting to biological results fast And there, I think there is seriously a possibility, as you say, with the improved resolutions in the upcoming years in those niche novel areas, there is definitely a possibility that, clean room may not be required for some of these devices.
Yeah. I mean, are you familiar with the book, The Innovator's Dilemma?
Yes, one of my friends gave me that as a wedding gift, actually. Yes.
Yeah, it's one of my favorite books, and it's a great example where, what is it about the 3D printing non-clean room approach that is beneficial to a certain technology or application, where the clean room stuff, while amazing, is just overkill.
Exactly.
Right. And you find where those niches are, and then you expand on those niches, and no one wants to pay the extra money for the clean room thing if they don't need it.
Exactly.
Right. So, and if anyone's listening and they don't, well, I hope a few people are listening, but for those who are listening, if you've never read The Innovator's Dilemma by Clay Christensen, who's at the Harvard Business School, I highly recommend that you read it. It is a phenomenal book about innovation and how new technologies emerge, and also how established companies fail to see them coming. It's really a fantastic book.
Absolutely. Second that. It's a great book. And yeah, for people that are listening, you should definitely, and are interested, you should definitely read it.
Okay, so in the interest of time, I'm going to ask you one more question. I like to end on kind of a non-technical question. And so you've had a lot of experiences over the last several years as a student, as an employee at startups, and now as a faculty member. So knowing what you know now, what would you tell your former self to do differently?
When you say former self, are you talking about my undergraduate self, or
yourself at any point in your life? Maybe it was your high school self, maybe it was your undergraduate self, or your graduate self. Where is there something you know now that you would go back at any point and have done something differently?
Oh wow. I maybe I would go back and most people in academia, maybe you're one of those people that went from undergrad all the way to their PhDs and either a short postdoc stint and then joined your faculty position. So maybe I would have, if I were to go back and talk to my 2000 and early 2000 self, maybe I would have go back and tell myself, be more. You should have gone straight to a PhD. I always had that doubt whether I should do this or not for a few years, and that's what took me some time to decide and get on the PhD track. So I would certainly go back and tell my master's self, go directly into a PhD. Maybe to my undergraduate self, I would say pay more attention, you should have taken more classes in material science and processing.
Yeah.
As an electrical engineer, that's not something that's taught a lot. And I got my undergraduate degree in India, and we barely touched any of those things. So I would go back and tell myself, take more classes in materials.
I would do the same thing, but apply to electrical engineering. As a chemical engineer, right now I'm dangerous with electrical engineering concepts. I know just enough. And luckily I have really good colleagues who steer me back when I'm going off a cliff. But I would say something similar, but applied in the inverse direction.
That's funny.
So Swami Rajaraman, thank you so much for taking a few minutes today.
Thank you so much, Mike. I really, really enjoyed it, and I appreciate the opportunity to come and talk on your podcast.
You've been listening to Nanovation. If you enjoyed the show, please leave a rating or write a review on Apple Podcasts. Show notes are available at fillerlab.com/nanovation. Nanovation is recorded in the Marcus Nanotechnology Building on the campus of Georgia Tech. Andrew Cannon edits the show. I'm Mike Filler. See you next time.